Hello, everyone, and thank you for attending the webinar. My name is John Stancarone. I'm an engineer and product specialist with T Equipment. We have a really great webinar for you today. Liz Makeley, application engineer with Tektronix, will be presenting when to use an oscilloscope versus a DMM. Liz has been with Tektronix for 6 years and has supported most of the benchtop DC measurement portfolio during that time. Before turning the presentation over to Liz while we're waiting for any late joiners to the webinar, I have a couple slides about our company to show you. Now, we've just celebrated recently 21 years in business, and in that time, we've become a very large stocking distributor. We really do take to heart the slogan, buy from people, not just the internet, and we have a qualified staff here that's happy to help you. Now, as you can see from this slide, as a national and international distributor, we cover the needs of a wide variety of customer types, all listed on the left side there, that left column. On the right, you can see some examples of the product and instrument types we carry. In total, it's more than 500,000 products that we distribute. And our company has invested heavily into our website, making it a great resource for research and shopping. Here you can see the filtering capability there on the left-hand side. When you click on those little down arrows, it opens up the ranges that you can select for price, bandwidth, channels, in this example, sampling rate, etc. So you can see that that allows you to really narrow your search by those criteria. We utilize an internal portal as well that we have built ourselves for better customer service, and we're constantly enhancing our website and internal systems to provide a better experience for our customers. Now, without further ado, it's time to turn the presentation over to Liz. If you do have any questions, please ask them through the chat feature, or at the end of the webinar, Liz will be answering them at that time when the webinar is complete. Hi, Liz. Thank you for joining us today.
Thank you for having me. Let me get my screen up. All right, looks like I got everything set to go. Well, thank you all for joining me. This is an explanation of when to use a DMM versus oscilloscope. As you can hopefully see behind me, I've got a couple instruments here. I have some DMMs, I have a scope. But you know, if you've done any kind of electrical testing, you've probably used these tools before and you know what they look like. But you may not know kind of when is the optimal time to use them. So before we get started, I'll do a quick kind of agenda. What are we going to cover? We're going to talk about each of the instruments themselves, what they do specifically, some similarities and some differences between them, and then what better to explain the differences than do some application examples. So we'll go through that. So scopes and DMMs, like I said, two of the most common test instruments and probably the most common test instruments when it comes to doing measurement. In order to understand when is best to use these tools, we need to know how they function and what they do. So digital multimeters are instruments that are used to make a variety of measurement, hence the term multi in the multimeter. They are a measurement only device and they typically don't provide any kind of user controlled sourcing function, although some of the functions in the DMM, like to measure resistance, do require a current source. It's not anything that the user has control over. The most common functions used with DMMs are things like DC voltage, DC current, and resistance. Most modern DMMs also have a lot of other measurement functions, such as AC voltage, capacitance, temperature. You know, there can be diode characterization things. And also, if your DMM has built-in math functions, you may be able to program it to read other additional sensors like transducers, making your DMM a meter that can measure something like strain or humidity. Another nice thing about DMMs is that they come in a wide range of capabilities and form factors. DMMs can go all the way down to those little tiny 3.5-digit handheld versions, all the way up to a rack style that's high density for an automated system like our DMM 7512, which is there at the bottom. For the most part, DMM functionality is similar regardless of the model. The main difference from model to model is in the resolution and accuracy of the DMM. So some applications only require you to do a basic spot check on the system, and it's not really worth paying for super high accuracy or high resolution because you're just not using it. But if you're trying to make low level measurements or measurements where you need that high resolution, you're going to need a DMM with more digits and better accuracy. Of course, the measurement you want to take is a factor. Basic DMMs may not have a dedicated function for trying to do something like temperature, and higher end DMMs will have additional features, like I mentioned, the math capability. Programmability and usability is always a factor when you're purchasing equipment. The handheld DMM has dials to change functions, which is great for, that in the field use. But our DMMs, like our graphical touchscreen DMMs, which I have over here, have buffers and graphing capabilities built into them, which make them a much more versatile system for doing more detailed testing, as well as being remotely controlled as well. So that's a DMM. What about oscilloscopes? So scopes are also measurement devices, although now higher end modern scopes will often come with arbitrary function generators built in. But the scope itself, that's an extra feature. The scope itself is just measurement. They are great for visual display of signals because they're making measurements based on time rather than a single point measurement. I'll talk more about this later when we compare the functionality of the two instruments. Scopes only make voltage measurements. So if we want to make a current measurement, we have to connect a special kind of current probe that converts that current signal into a voltage signal that then the scope can read. This is different than a DMM, which actually has multiple different circuits built in to make various measurements. There is an ammeter circuit in the DMM versus the voltmeter circuit. With the scope, we have to include external hardware to make that conversion. Like DMMs, scopes also come in a wide variety of options and form factors. They're heavily used in diagnosis purposes. So a lot of them are benchtop style because they're kind of meant to be on your bench. You can kind of poke around with things. But there are also selections for handheld and portable scopes, like our MSO2 series has an option for a battery pack. So, it can be kind of carried around if you're working with a very large system, like, a whole car or something where you don't have a benchtop surface. And I've also seen oscilloscopes be worked into racks. So you have lots of different options to go with there. All DMMs function similarly pretty much, but actually scopes, there are a lot of different kinds of oscilloscopes and a lot of different features in them. So you really have to choose the one that works best for your application. Digital storage scopes, or DSOs, are your kind of conventional basic scope. They're really good for capturing transient signals and other generalized signal events. The digital phosphor scope, or DPO, is a more advanced version. So it uses parallel processing to increase waveform capture rates so that you get more detail in the signals that you're capturing. Mixed domain scopes combine that oscilloscope functionality with RF spectrum analyzers, and mixed signal scopes are the oscilloscope functionality with a logic analyzer. So I think MDOs and MSOs are kind of, when we think about the mainstream scopes, that's sort of what I think of an MSO. So that's actually an oscilloscope and logic analysis. So both of these scope architectures extend the range of signals that they capture and evaluate. And then finally, digital sampling scopes achieve much higher bandwidths and higher speed signals than more traditional scopes. But the trade-off is that there is a much lower voltage input range for that. So, again, you get more features, but there's some trade-offs there. And you sort of need to decide what are you actually trying to measure with that. There are a lot of features to consider when you're selecting a scope. A lot of different specifications, including bandwidth, waveform capture rate, sample rate, and rise time. All of these are going to contribute to how accurately your scope is able to measure and capture the waveform. The closer you are to the limits of what the scope is capable of, the more your signal will be attenuated, and the more likely you are to miss out on the critical information that you are looking for in the first place. And of course, you want to make sure that your scope is convenient for you. It's, got the connections that you need. It could be controlled remotely if that's something necessary. A lot of our oscilloscopes at Tektronix have very nice, like large touchscreen panels, so they're very easy to use. So you want to have an instrument that you're going to enjoy using and get the most out of. So now that we know what a DMM is and what an oscilloscope is, how do we select one to use? Because, a lot of times I get customers who are like, I have a scope, I don't need a DMM, or, vice versa. So, how are they similar and how are they different so that we know when one tool is better than the other? So like I said, both of these tools are measurement devices. Standard versions of these instruments are not going to provide any kind of sourcing capability. So if you need a power supply, that's going to be a separate instrument. They can both be used to measure DC and AC signals. There are some limitations that I'll get to in the differences. DMMs can't do everything that scopes can. So, there wouldn't be a point in having separate tools if they could. They're both great tools for debugging circuits, which is why they are such common bench tools. And some of their functionality can overlap. Like, you can take single point measurements with with a scope similar to a DMM. Like some of them will have literal DMM functions in them, or like a voltmeter function. And newer modern DMMs can have digitizer functions that mimic the capabilities of a scope. So we're going to see more of this in a bit. How are these tools different though? I like to consider it in terms of pictures versus numbers. So scopes are visual tools. The whole point is to show the waveform as a picture. And DMMs are what I like to think of as number tools. Their goal is to show you the value of the measurement. And this goes along with the idea that scopes are time-based measurement tools. They're taking many measurements over time to see how waveforms are varying, whereas DMMs are taking measurements in an instance of time. So if we want to know what the voltage is in the circuit right now, give us that one single value. Because of this differentiation, scopes are more optimized for AC behavior because that's behavior that's changing over time. They are built to operate at much higher frequencies and make measurements on much more complex waves. So they have a lot of like noise canceling capabilities and isolation, things like that, to really visualize that whole waveform, whereas DMMs are optimized to take single clean DC measurements. The trade-off there is that DMMs do the DC point measurements much better than scopes. They tend to have better accuracy on that, and I'll explain that a little bit more later. So let's actually take a look at some examples. So say I want to measure component behavior or characterization, like say a MOSFET. Oftentimes when we're doing this, we are looking to characterize a voltage or current on the device with respect to other conditions in the circuit. So when I take a MOSFET characterization curve, we might have a power supply power the gate and drain terminals of the FET and then use a DMM to measure the current as the gate voltage is changed. In this case, we are not concerned with how the voltage is changing over time. We're concerned with those discrete DC measurements at each voltage point that we are sourcing. So the DMM is more accurate of the two for measurements like this, which brings us to the question of, why is a DMM more accurate? So oscilloscopes are optimized for high-speed measurements because what we want to do is visualize that behavior. And to accomplish this, we take a series of samples of the waveform and connect them all together. And you can do this with a DMM as well, or any measurement device that takes more than one measurement. But in order to do that, those instruments are taking very fast measurements. And DMMs are actually optimized to take slightly slower measurements because they are using an integrating A to D or analog to digital converter. And what that does is it takes a bunch of samples and basically averages them together. So if you've ever used a benchtop DMM and seen a setting called NPLC, number of power line cycles, that is what that means. That is the amount of time that we are going to integrate the waveform and send back a single measurement from that integration. And the reason we do this is to eliminate, uh, 60 hertz or 50 hertz if you're in a different country, 60 hertz line noise, which is the noise coming out of the power circuits that we all inevitably have to deal with if you have an instrument that plugs into the wall. So by doing that, we get slower measurements, but we also get more accurate measurements because we are eliminating a lot of that noise. Um, this isn't to say that your scope is inaccurate because it is not. Scopes are definitely advancing in accuracy, and they are great measurement tools. But if you're trying to get the most accurate measurement of a DC signal, you are probably going to get better performance with a DMM over that scope. For example, a DC voltage measurement on a scope for like 1 volt might vary by up to 10 millivolts. That's would be the inaccuracy levels, whereas a DMM might have accuracy down to 10 microvolts. So, if you're in an application that needs that level of accuracy, a scope is not going to be the tool for you. Going back to my example for just a moment, there are some exceptions to using DMMs for device characterization, and that would be when you are trying to characterize high frequency behavior or behavior with respect to time. So if you're looking at a capacitive or an inductive load for filtering behavior or a transient behavior in a device like a turn on or turn off waveform, that is where a scope is going to come back into play because we are dealing with variation in the signals or something, excuse me, that requires a higher frequency. So that is so FET transient behavior is a good lead into a great application for scopes, which is debugging signals and waveform behavior. There are so many reasons that you might want to do this. That could be excessive noise, that could be timing jitter in the signal, runt pulses where you don't reach that threshold for high to low in like a TTL type application, that might cause errors in a binary data transmission. We are always concerned with understanding these transient behaviors because we would like to prevent them. They are erroneous in our signal. Um, and, for things like a wide bandgap MOSFET that's turning on and off, we would like to know how quickly that's happening. So, all of these things, I don't think there's an electrical engineering application out there that wouldn't require some kind of debug for problems, unfortunately. So the best thing to do with this is to use a scope. So again, these are optimized for the high-speed sampling and signal visualization. So many transient behaviors are occurring over a very short period of time, nano to microseconds, and we need that high sampling rate to capture that behavior. With a DMM, we might not even see a change in the readings on the front panel before that transient has moved on. And the DMM's still settling and completing the reading, the transient's gone. And so sometimes you can measure a system with a DMM and think nothing is wrong, but it's still not working. And then you get out the scope and see, oh, I'm getting so much noise that I'm not witnessing because the measurements are integrating it out. We have the same issue with anything that has a high frequency data transmission. Scopes are great for debugging actual data transmission. Like I know we have a feature in one of our scopes to do CAN bus. And it'll actually decode the whole waveform. The DMM just cannot measure it fast enough to get an accurate picture of the signal. And what's really nice with having some of those features is sometimes the scope can give you a presentation of what the data was, and you can see, oh, here was the error. So one way to get around this is if you have a DMM that has a digitizer. So what is a digitizer and a DMM? It's basically an alternate A to D. So rather than the integrating A to D, we're using a sampling A to D. And this is going to take much faster measurements. Typically up to like a megahertz sampling rate. So, you can measure things that are more AC in nature than you would with just the regular integrating A to D. So this does, whoops, go back here. There we go. This does involve a dip in the accuracy and precision. Anytime you increase speed of measurement, you're going to lose a little bit in the accuracy. But that sometimes is really worth the trade-off. So I'm showing on the screen here captures from our DMM 7510, which is one of our touchscreen models. It's a 7.5-digit DMM, and it has a built-in graph utility, so you can see the data that we're taking live, which is really nice. The bottom left image shows digitizing voltage and current on the turn-on characteristics for a DC to DC converter. We want to characterize the transient behavior of devices when they turn on and turn off like this, because it's not an immediate thing, and there might be some noise in that. On the right side, we can see comparisons between the digitizer of the DMM 7510 and the scope to measure ripple voltage on that DC to DC converter. If we look at peak to peak voltage, the ripple is only about 6 millivolts. And this actually is not evident on the scope when it is DC coupled. Because you have that offset, and the scope is the resolution isn't enough to see that, whereas the DMM can measure still with that resolution even while having a DC offset. We can do AC coupling with the scope and see that ripple, but we still aren't able to achieve the same accuracy and visualization for such a small signal. It's not as good as what the DMM can do. So anything that is within the bandwidth of the digitizer, in this case, because our DMMs are set to digitize at a maximum of 1 megasample per second. Signals that are in kind of the hundreds of kilohertz ranges or lower are about what we can measure as far as AC frequency. Anything above that, you're going to have to go to a scope because we just can't sample fast enough. Sometimes we want to take a DMM measurement, but the DMM measurement wasn't what we were expecting. So this is a similar case to debug a circuit that, again, if our DMM measurements aren't quite working, well, is there noise or something that is getting incorrectly integrated into the measurement? A great thing to use is a scope, because we also have spectrum analysis tools that can show us kind of where is the noise, what is the noise doing. A true story, we had a customer who was experiencing very noisy measurements on their DMM. We were able to take a scope in, measure the noise present in the environment, which we found to be very unusually high. Like we were seeing 7 volts or something, and we were like, okay, that's definitely not going to work. In this, in the case of this customer, and in the case of a lot of these situations, these can be like manufacturing environments. We have a lot of equipment going. The power line input may be very noisy, and the scope was enabled us to see exactly how much noise was present, and give us some options for what we could do to help clean up that DMM measurement, like putting on an external filter to filter out some of that high frequency noise. If what you're looking to measure is a type of AC voltage signal, you can use either depending on what you want to do. So if your signal is pretty close to a sine wave and you just need a frequency or an RMS voltage, you can use a DMM. Most of them come with that kind of functionality. But if you are measuring anything that isn't really a sine wave, that's a high frequency, like I said, something more than a couple hundred kilohertz, or you want to make measurements like a peak to peak or a rise time, any of those, you're going to need a scope for that. All of that stuff is built into the scope already. As circuits increase in complexity, we oftentimes want to measure more than one thing. Again, both of these have the ability. So most oscilloscopes have multiple channels on them, and these are measuring in parallel. You can see I have 2 signals up on the screen at the same time, whereas DMMs are typically one channel. So there's only one input coming into this instrument. It's only measuring one thing at a time. We can kind of cheat the system a little bit using something called a switch card. Oops, that was on the same slide. And basically, all that is a set of relays that's going to route the signal. The most common kind of switch card is a multiplexer, and so you have it one input signal, or you have multiple input signals connected to channels, and then the channels switch and route the connection to the actual measurement circuit. And this is nice because you can take the one channel of the DMM and measure multiple devices on it without having to sit there and unplug your wires a bunch of times. So those are typically used in high density automated systems. So hopefully I have convinced you of the merits of using a DMM or a scope for your application, but it's a good chance that a lot of you out there will need both. Tektronix and Keeley have a great portfolio of both DMMs and scopes. I just want to highlight a couple of our, kind of basic instruments to take a look at. Our DMM 6500 is our graphical touchscreen model. I have it sitting right here. It's a wonderful DMM. It's a 6.5 digit. It's a great multi-purpose tool. And then our 2 series MSO scope, this is our low profile 2-channel scope. It's got a pretty good bandwidth range, up to 2.5 gigasamples per second. So again, it's got, kind of a good range of functionality for an entry level application. Just to summarize the things that we covered today, you are going to want to use a DMM for anything that is DC, low frequency, especially things where you are caring about the value of the signal or the value of the signal with respect to other signals in the system. They are great general purpose tools. And for scopes, you want to use those for anything that is high frequency, anything that is complex signal wise, anything that you want a time-based or a frequency-based measurement. For example, something like rise time, transient behavior. They are great tools for advanced troubleshooting and debugging, and they have a lot of additional features to fit your application. But in reality, both tools will have a great place on your bench, and you'll get a lot of use out of both. And the hope is that with all the knowledge you've learned here today, that you'll know when to pick up your DMM probes or your scope probes. If you have any additional questions or concerns about, how do I use things, we've got a lot of resources on our webpage. T Equipment has a lot of resources, so those things are out there. I just want to draw your attention. We have data sheets for those 2 instruments that I mentioned, as well as a XYZs of oscilloscopes primer. That is a lengthy but very detailed and a very comprehensive overview of the functions of an oscilloscope, and then a selector guide for our digital multimeters that covers, general specs and options, and kind of some comparisons that'll help you sort of know what you're looking for. And with that, I want to say thank you so much for attending. I hope you learned something out of this, and yeah, I hope you enjoy using your measurement equipment in the future. So John, I will hand it back to you. Awesome. And then I don't have your audio, John.
Okay. Thank
There
you,
we go.
Liz. Yeah, I was on mute. Thank you very much. Well, that was a very informative webinar.
Thank
We
you.
do have a few attendee questions for you, so I will read those off to you. Now, if anyone else has any other questions that come up, please submit them to us via the chat feature in the webinar, and Liz will be happy to answer them for you. Okay, so the first question we have, Liz, is could the digitizer on the DMM be used to measure something like peak-to-peak voltage, a useful and very common measurement?
Yeah, so that is a good question. You could extract that kind of measurement if you wanted to. If you think back to the screenshot that I had showing the ripple voltage, you can, take a measurement at the top and the measurement from the bottom, subtract them. But you would have to do the calculation. What's nice with the scopes is they oftentimes have peak-to-peak functions built in that you're just, hitting measure peak-to-peak, and it'll do that calculation for you. But,
Right, very
you
nice.
can do it if you already have the DMM.
Sure, yeah, great, thank you. The second question we have is why is the sampling rate a concern? for a scope?
So, if you've heard of the Nyquist theorem, this goes back to like how fast you have to sample in order to completely reproduce a waveform.
Right.
Believe the formula is you have to be twice the frequency of the highest frequency component of your signal. Otherwise, you are going to lose data, lose parts of your signal. So, if you're trying to measure a signal at say 100 hertz and your sampling rate is also 100 samples per second. I mean, granted these are very low numbers to do math. You're going to miss out on part of that data. You aren't going to see the full picture, and you won't be, you might miss out on the thing that you're looking for, either that error or that behavior. So it is important to ideally have an instrument with a sampling rate that is much higher than the signal frequency that you are trying to measure.
Got it. Thank you. That's interesting. Now, the third question we have is, if my DMM does not have a digitizer, should I always be using a scope for measuring and analyzing AC waveforms?
Pretty much, yes. So higher end benchtop DMMs will have some speed settings, like our DMMs can go down to 0.0005, 0005 NPLC, which gives you a measurement rate of, I want to say, somewhere around like 100 microseconds, or yeah, about 100 microseconds per reading. So you can get some flexibility with that, but really, if it's not DC, a scope is going to be the better option. Save for anything that's pretty low frequency.
Got it. Thank you very much.
Yeah.
Well, it looks like we don't have any other further questions at this time, so we're going to end the webinar. But if anyone does have any questions that come up after the webinar is concluded, or if there's anything else that we can help you with, please do not hesitate to reach out to us via the contact information shown on the displayed presentation slide. I want to thank everybody again for attending the webinar, and Liz for presenting. That was fabulous. And everybody have a great day.
Thank you.
You're welcome.